Good afternoon everyone. I am Chanda Devnath, one of the PMRF fellows of ISET Berhampur. I am the TA of this course Retrosynthesis in Organic Chemistry. Here I usually discuss about the topics or some name reactions which may help you to solve or predict the retrosynthesis of any compound. So in the previous classes I have already discussed about all the name reactions, important one, and also I have discussed about all the different type of reaction mechanisms like substitution, elimination, etc. In the yesterday's class I have discussed about the retrosynthesis of some important compounds, some natural and also some biologically important compounds like aspirins, the medicinal compounds. So today I will discuss the same retrosynthesis of some other compounds and how we can predict the inertia selective synthesis of any compound. So if you are interested to know about those classes, you can go and check. Videos have been uploaded by NPTEL, I think. The link has been shared by them. You can go and check. So let's start. Today is our last class. So if you have any doubt regarding this one, you can contact me. The slides and videos are uploaded. Links are shared. So you can go and check. This is the last class of this session. So today I will discuss about what is retrosynthesis, that one we have discussed earlier also, and retrosynthesis of some important compounds. So what is retrosynthesis? This we discussed yesterday also, but just for a recap I am discussing again. Retrosynthesis is a technique which chemists use to identify how to synthesize a molecule through approaching the problem backwards. Effectively, retrosynthesis starts from the wanted product and works backward, chopping and changing the molecule into smaller pieces to identify what was the previous molecule can be made from. These chopped molecules are referred to as synthons and are usually unstable ions. Thus, it is important to identify a molecule, stable equivalent molecule, that is called synthetic equivalent, and which would react in the same way. So the trick to a good retrosynthesis is knowing which bond should be broken first, and that knowledge can be gained just by practicing more and more questions. Because how we can determine in a compound or unknown compound to plan the retrosynthesis which bond should be broken first. For that you need to know about some previous questions. Based on those previous idea, you can get a call. You can take a call that okay, this bond can be broken first. So what is the arrow of this retrosynthesis? This bold arrow denotes that bonds are broken. There is no such reaction has been performed. This is a imaginary process that we are breaking any bond, and how this can be formed. This is an imaginary process. No such any practical reactions is not getting performed while showing this bond. While showing this arrow, it means there is no such practical reactions is being performed. So yesterday I gave a homework and I told you to try this one by yourself. We will solve it together today. So I don't know how many of you have tried. So let's start. So first, you can see there is a ether one. There is a ether. Ester, alkene. Now which bond should be broken first? So you can see this is a benzyl group. Incorporating a benzyl group to a hydroxy group is quite easier process. So we'll first break this bond. We'll first break this bond and get a alcohol and a benzyl bromide or any benzyl with a leaving group. So we'll get this alcohol and a benzyl with a benzyl group with a leaving group. So we'll first draw the retrosynthesis of this part. Now if you can see, this is a 1, 2, 3 substituted. So if you plan the retrosynthesis of such compound and break this bond, how can this form? It can form by simple enolate reaction, because this is a enolate ester. This part can be a enolate ester. So if you just break this bond, what we will get? If you break this bond, there will be a positive charge here and a negative charge here. And if you draw the synthetic equivalent of such, if there is a positive charge and draw another alcohol, 2-geminal alcohol is denotes aldehyde. So you can substitute this aldehyde, and as there is a negative charge, if you give a H, it will give this ester, methyl ester. Now if you want to, now this can be also synthesized. So if you plan the retrosynthesis of this compound, this is also a 1, 2, 3. Whenever there is a 1, 2, 3 substituted, there can be a, you can just break this alkene, one bond of this alkene, and functional group interconversion, and incorporate a OH group here. Now you can see this compound is quite similar to it. Whenever there is a 1, 2, 3 functionalization, what you can predict? It can be, this bond can be broken, and you can predict that there can be a formation of enolate. So if you break this bond, it will be aldehyde. Another part, this will be also an aldehyde. So this product can be formed through self-aldol reaction, self-aldol condensation. So this can be formed through a self-aldol, and if you perform condensation, this OH will be eliminated and we will get this one as our product. Okay. So if you predict the forward synthesis of this compound, okay, before that we have said that there will be a benzyl group. Now if this can be a benzyl bromide, or a benzyl alcohol. Now the question is, which one we will choose for this one. Now we know, if we choose this benzyl bromide, after this OH attack to this benzyl position, HBr will be eliminated, H from OH and this Br. So the medium will be bit acidic. The medium become quite acidic. And we know, in presence of acidic condition, esters are not stable. Ester will be hydrolyzed first. So Just to avoid hydrolysis of the remaining substituent, we will choose this benzyl alcohol. We will choose this benzyl alcohol. Now the problem is, which is a bad living group? Which is a bad living group? If you just react with this alcohol and this benzyl alcohol, this will not react to give us this product. We have to make OH a good living group, and that can be done through adding this auxiliary type of this group, which will react first with this OH group, where this in presence of KOH, OH will be eliminated, then O- will attack to this carbon center. After that, it will form this benzyl trichloroacetamide. This group is a good living group. This group acts as a good living group. Now if you react this one with the alcohol, what will happen? This alcohol will attack to this benzyl position, and this part will be eliminated, and we will get our benzylated product. Another advantage of using this trichloroacetamide is the byproduct which we get through this one. This is quite stable amide and remove, and it crystallizes easily, and it crystallizes easily. Because of that, this can be removed from the reaction mixture easily. So that there is sometimes there is a problem that byproducts are also soluble in the same solution where the product is soluble. In that case, it is very difficult to separate. But here, as this can be crystallizes, so we can separate this one easily from our desired product. Now let's plan that what will be the forward synthesis of this compound. So what will be the forward? We will start from this aldehyde. We will start from this aldehyde. And we will go through this path. So let's plan what will be the forward synthesis. So we will start from this aldehyde. If you take 2 molecules of this aldehyde and under aqueous NaOH and heat, it will give this alkene. Now if you react with this one with OET, plus NaOET, NAOT will take a proton from here. This will take a proton from here. Will be generated here. Enolate. Then this enolate will come back and attack to this center, to this position. Give us this alkene. Now, if we react this alcohol with trichloroacetamide, followed by presence of KOH, followed by KOH, it will give benzyl alcohol, it will give the target molecule as our product. Now let's go to the next question. How will you predict the retrosynthesis of this compound? How will you predict the retrosynthesis of this compound? It's a very easy compound and small. So first, as you can see, there is a 2 ether group. So this 2 ether bond can be broken, and there will be 2 OH, and this part can be part of a acetone. So the first step can be done, that we are just deprotecting this acetyl group. We are deprotecting this acetyl group. We are getting 2 OH and 1 molecule of acetone. Now in the next step, what you can do, we can can change the functionality of this group with an aldehyde or ester. Now see, this is a 1, 2, 3 substitution functional group. So what we can do, we can perform the enolization reaction. We can perform a enolization reaction. So if we just break the bond from this side, what we will get? You can get a enolization. So if there will be aldehyde and a enolate. Okay, so it was simple. So what will be the forward synthesis of this compound? We will start from a dimethyl bromoester and under zinc condition. This is the in presence of zinc. This is a Fabovsky reaction. So in presence of zinc, it will form a zinc bromide. ZnBr, and that carbon will be partially negatively charged. So this nucleophilic carbon will attack to this aldehyde group and form this alcohol. After that, this ester group can be reduced to another alcohol. Ester group will be reduced to alcohol. After that, if you add acetone and small amount of acid, this 2OH will be protected through acetone and give us our target molecule. Understood? Let's go to our next question. Show how the relationship between the alkene and the carboxylic acid influence the suggestion for the synthesis of 3 compounds. So see, all the 3 compounds have a alkene group and the acid group, but the difference is the position of the alkene with respect to the acid. In this one, the alkene is at the alpha beta position, whereas in this case this is at beta gamma position. In this case, this is gamma delta alkene. Okay. So what will be the difference in the synthesis of this such compound? In this case, for this alpha beta unsaturated compound, this can be easily formed through a aldol condensation. Whenever this alpha beta unsaturated ester or acid that can be synthesized to easily form alpha beta aldol condensation. So if you just form the aldol, it will be OH. So replace this with so it can be easily formed through such process. So what will be the forward synthesis? If you take this aldehyde and this ester and perform aldol condensation, it can be performed through aldol condensation and also by Fabovsky rearrangement. Let's take the Fabovsky one, that will be more selective, because in case of aldol, this is also aldehyde, there is a probability of reacting this as also alpha hydrogen. So if there is a probability to take this alpha hydrogen instead of alpha hydrogen of this ester, so make this more selective, we can perform Fabovsky rearrangement. So what we can do, what will be the process? You take this aldehyde and this alpha bromoester, you first in presence of zinc. This will give zinc. In the second step, if you just hydrolyze it with acid, it will give this alpha beta unsaturated acid. Now the next one is beta gamma. This is a bit difficult because there is a high chance of this double bond to shift at this place to get in conjugation with this acid. So there is the only way to form this, if you break this acid bond, there will be a bromine, and if you just substitute this acid with the acid equivalent, that is Cn minus, this can be formed. The Cn minus will attack here and Br will be eliminated. After that, through acidification, we will get this acid. Understood? I am not showing the forwards, this is easy to understand. If you just have to take this allylic bromide, in that one, if you just add KCN minus, this will be eliminated, substituted by this Cn minus, and after that, if you perform hydrolysis to H3O plus, then this will be hydrolyzed. This Cn will be hydrolyzed to CO2H. The next step is gamma delta. So to synthesize this gamma delta acid, see the functionality is 1, 2. So if you just break this bond and take allylic bromide, this will be a diethyl oxalate, diethyl malonate, we will get this gamma delta as our product. Okay, so if you want to incorporate a CO2H group, what will you use? You will use Cn minus. If you want to enhance one carbon, we will use malonate ester, diethyl malonate ester. So what will be the forward synthesis of this compound? If you just take allyl bromide, and in that if you add diethyl malonate, and perform followed by hydrolysis and heating. In that case, after this substitution, both the CO2 group will be CO2H, and due to heating, one CO2 group will be eliminated as carbon dioxide. Okay. Let's go to our next question. What will be the retrosynthesis of this compound? See, there are 3 chiral centers, so we have to perform the reaction in such a way that this product form in an enantioselective manner, so that the chirality of these centers are intact. So first, this is ester group. So we'll just, whenever there is a ester, that's very easy to cleave because it can easily form. If you cleave this one, you will get this acid and this alcohol. Now if you want to see, this alcohol is 1,4 diene. So that can be formed through Barch reduction. So if you just perform the Barch reduction of this compound, you will get this 1,4-diene. So you don't know about the Barch reduction. In case of Barch reduction, this 1 electron from sodium will attack to this benzene ring. The double bond will shift. Will attack here, double bond will shift and enter as a, and give a electron here. After that, it will take a proton from the proton source, that is liquid ammonia or ethanol, and it will take another electron. After that, this will also take a proton and we will get this 1,4-diene. But whenever this benzene ring is substituted, there is a pattern that where the single electron will attack first. So if if the benzene ring contains, I have talked about this Barch reduction in one of my videos separately. You can go and check there. I have talked about this Barch reduction in my video separately. You can go and check for more details. Here I am just give a short idea. Whenever there is an electron withdrawing group, in presence of electron withdrawing group, which positions are more electron deficient? Alpha and gamma. Not alpha, gamma. This ortho and this para position are more electron deficient. So electrons preferably attack to this ortho and para position. Ortho or para position and shift the electron density. So, but in case of electron donating group, which position is more electron deficient? Obviously the meta position. So the first electron attacks to the meta position and shift the electron density in this way. Okay, so now to get the 1,4 addition, see, if we if you consider this one as this is a alkyl group, the acid group is not directly connected. So if you have to consider this as an alkyl group. So if you consider this alkyl group as an electron donating group, so which is the meta position of this one? This is meta. Whereas instead with respect to this one, this is meta. So if electron attacks at this position, the electron cloud will shift this way, but if the electron attacks at this position, the electron clouds will also shift this way. So if whatever the side you choose, you will get this 1,4 diene. So there will be a Barch reduction. Okay. Now next is how we can incorporate this acid group. If we just break the bond from this side, you will get a benzyl bromide, which can be substituted with the CN and that can be acidified later. Or another process is, if you take magnesium bromide, it will transform into a Grignard and react with carbon dioxide, you will get this acid. Now how we will get this bromide? If you just take orthoxylene and perform Br2 then H-nu. In such condition, one of these CH3 will be get brominated and will give this benzyl bromide. There is another way to get this acid is there. If you just start from alcohol, you just start from an alcohol. Then how can this get, if you acidify or if you just oxidize this one in presence of formic acid and strong H2SO4, it will give acid. Now how we can prepare this alcohol? The bromine and CO2 and HCHO. If you perform the Grignard and it attack to this formaldehyde, you will get this alcohol. There is another process, and this bromine can be formed through xylyl orthoxylene in the similar way. So there are two processes to make this 1,2 disubstituted methyl ester acid. Now the thing is, we have got an idea how to prepare this part of this compound, how to prepare this part of this compound. Now the another part is this one. How will you get this compound, this part? How will you form this one? Okay, this part is clear, right? Up to this part is clear. How will you get, we can form this acid part. Now the thing is that there is a chiral part which is this containing this cyclopropane and an alcohol. How will you get this one? So that we will discuss. We have discussed up to this. Now if you take this one, there is a syn cyclopropanation. that cyclopropane is forming from the same side, and also from the side selectivity. See, both the H are above the plane, and this OH is also above the plane. That means the cyclopropanation is forming from the below the plane, just opposite side of this OH. Understood? Because the two OH are above the plane, which is the plane of the OH. The two OH are aligned where the OH is there. That means the cyclopropanating reagent is approaching to the alkene from the below the plane. So if you take this alkene and if you rotate this one to get the preferred configuration, rotate this bond. If you just rotate this bond, and OH will be below the plane, so that the reagent comes from the below the plane, because reagent is coming from cyclopropane is forming below the plane. So if you just rotate and transfer this OH to the below the plane, then this part will go to the above the plane. So this reagent will come to the below the plane, and we will get selectively this as our product. Now how we can form this alkene? If you take then this alkene can be substituted with the alkyne, and if you perform a linear reduction through a linear catalyst, it will selectively reduce this triple bond to double bond in a seen manner. Now how you can form this one? You break this bond. This can give a acetylene group, which can be deprotonated by using any strong base like butyl lithium, and it can react with this aldehyde to give this alcohol. Okay. So let's see the forward synthesis of this compound. If you take this aldehyde in presence of so what will be the forward synthesis of this compound? First you have to take this acetylene group. This acetylene will be deprotonated by using butyl lithium, and that will attack to this aldehyde. Then we will get this alcohol. After that, if you perform reduction using linear catalyst, you will get this alkene, and in presence of cyclopropanation, we will get this cyclopropane compound. And for the another part, what you can do, you can take a xylene, and if you perform a bromination, it will give this this alpha bromination, and this can be substituted with the CN to give this CO2H. Another way it can be reignite and react with this CHO to give this alcohol, and alcohol can also be oxidized to acid. Then it can undergoes a Birch reduction to give this 1,4 alkene. Then after that, these two parts will combine with each other to give us this product. So how will you plan the retrosynthesis of this compound? So here you can see there is a amide and there is a thio group. So if you just break this bond first, or this one first, what you will get? There will be a bromine. After that, substitute this bromine with OH. What will you get? We are substituting this bromine with the OH. Next is we can substitute this OH group with a ketone. With a ketone. Then if we just break this bond, what we will get? There will be acyl chloride and benzene. This can also perform from aniline and acyl chloride. Okay. So what will be the forward synthesis of this compound? First, aniline will react with this acyl chloride and pyridine to give this amide. After that, if we react with this through Friedel-Crafts acylation, it will incorporate into this para position and give us this 1,4 disubstituted group. Now if you just perform the reduction, the selective reduction of this ketone, that's why we are using NaBH4, because if you use LiLH4 there is a probability of reducing this amide also. So to perform the selective reduction we are using NaBH4. After that, then this will be OH to brominating. If you add PBr3, this OH group will be brominated to give bromine. And the next step, if you use thiourea, this bromine will be substituted with SH. Thiourea and NaOH, this bromine will be substituted with SH. So what is the mechanism of reacting this alkyl bromide with thiourea? That I have also explained. If you react this alkyl bromide with the thiourea, what happens? This S double bond attack to this bromine carbon center and eliminate bromine from the system. After that, there will be a positive charge. Now this NaOH will attack to this carbon center, break this, neutralize this sulfur. Now this is a very probability of breaking this bond, because the carbon oxygen bonds double bond is more stable than that of the carbon sulfur bond because of 2p2p overlap, and in case of sulfur there is a 2p3p overlap. So we know on always a 2p2p overlap. 2p2p means I am saying that 2p orbital and 2p orbital, 2p orbital of oxygen and 2p orbital of carbon. So the overlap between a 2p orbital of oxygen and 2p orbital of carbon is always favorable than that of the overlap between the 2p orbital of carbon and 3p orbital of sulfur because of the size mismatch. So the always, because of that, the carbon-carbon oxygen bonds are stronger than that of the carbon-sulfur double bond. So this is the driving force of this compound. So to form this carbon-oxygen double bond, this lone pair comes here and break the sulfur carbon bond, and we get this sulfur substituted product and urea as our byproduct. Okay. Let's go to the next question. So we have to plan the retrosynthesis of this compound. I have already shown. I will explain that one by one. So there are two ester groups. Now let's break the first. If you break this external ester group, what you will get? This there will be a OH and there is a acyl chloride. Now in the next step we are breaking the another ester bond. In this case we will get here there will be a ester and a OH group. Now if we just rotate this bond, this comes here and this goes here, then it will be below the plane. Now to form this one selectively, how we can form this? By, if you just, this is also 1, 2, 3 substitution, so that can be formed through an enolization reaction. So if you just break this bond, you can get this aldehyde and this ester group. So in presence of NaOH, this part will be enolizable and it will attack to this carbon center. It will attack to this carbon center. Okay. So this is the retrosynthesis. So what will be the forward synthesis? You have to take this aldehyde and react with, to take this OET, X as OET. Then we will get this diol system. After that it will undergo intramolecular cyclization. Through this OH will attack this ester group and eliminate this OET and form this 5-member cyclic structure. After this external OH will attack to this acyl chloride to form this target molecule. Next, I have also given this one as one of your homework. I will solve this one today. What will be the correct, this came on NET 2012. What is the correct sequence of reagent for effecting the following conversion? So to form this product from this substrate, what should be the reaction which should be performed in a proper manner or in proper step by step to get this as our product? From the options you can see the reagents are same, but in some options they are given first, for some they are given in the second position. So how will you choose the reagents to perform step by step to get this product? So before that, let's try to practice the retrosynthesis of this compound so that from there we can get an idea how we can perform this product from this substrate. So we have to go to this substrate through a retrosynthesis manner. So let's first break this bond. To break, there is an alkene, so we are breaking the alkene first. To break this alkene, how can this can be a ketone? there will be a negative charge which can be shown by this way also. I am showing this type of disconnection because we have to go to this substrate. This is not like we are just predicting anything. We have to go to this substrate. Now, see, if you just remove this O minus with OET, now if you just split this alkene, what you will get? There will be a OE carbonate. Okay, so see, this is similar to our substrate. This is same to our substrate. So now let's try to draw the forward synthesis. Try to draw the forward synthesis. How this can be performed. So if you want to make this carbonyl to a CH2, that can be performed through Wittig reaction or Tabbe reagent, you know that. But in presence of ketone, there is a high probability that ketone reacts faster because of its high electrophilicity. Because it is a better electrophile than that of the ester carbon. It is a better electrophile than that of the ester carbon. Because of that, it will react fast than that of this ester. So just to make ester react fast, what we will do? We will protect this aldehyde. We will protect this ketone. How we can protect that? By using ethylene glycol. So in the first step we will use ethylene glycol. So these two are cut already. We have to use ethylene glycol. So it will be the correct option will be between A and B. So we have to protect this by ethylene glycol. So in the first step, pH will be protected by using ethylene glycol, and PTSA, that is giving us H plus. PTSA, paratoluene sulfonic acid, this is giving us H plus. So this will be protected now, and ester is now. If you add, now we have to make this CH2. Now we know that the Wittig reagents can perform and react only with aldehyde and ketone, but Tabbe reagent can react with both, with all aldehyde, ketone and ester. So therefore, in this case we have to choose selectively the Tabbe reagent. We have to choose selectively the Tabbe reagent because Wittig reagent do not react with ester. It will only react with aldehyde and ketone. Okay. So we will use Tabbe reagent. So what will we get? TB reagent will make this a CH2. Now in the next, so from there option is already been selected, that option is A. Now let's perform the next two steps also. If in presence of H3O plus, this ester will be hydrolyzed as well as this one will be deprotected. Okay. Now in presence of base, this acid will be deprotonated. Now it has a great probability that it will come here, and this goes attack here. And to elimination of OH, get this as our proton. Okay, so the correct option is option A. Okay, so thank you everyone for attending my classes. All the videos have been uploaded. This one I will upload also. So all the best for your exam. Have a nice day.